Hello and welcome to this lesson on the Haber process. In today's lesson, we will first understand the process of forming ammonia via the Haber process using nitrogen and hydrogen. We will then recognize that the Haber process operates at specific conditions of temperature, pressure, and with the aid of a catalyst to maximize ammonia production. Finally, we will learn how the chosen conditions are optimized to favor the forward reaction while minimizing the reverse reaction, based on principles of chemical equilibrium and reversible reactions. So far, we've explored the fundamental concepts of reversible reactions and dynamic equilibrium. You are also familiar with Le Chatelier's principle, which helps us predict how changes in conditions affect the position of equilibrium in a chemical reaction. Building on this foundation, today's lesson will advance our understanding of how these principles are applied in industrial processes, specifically in the formation of ammonia through the Haber process. The Haber process is an industrial method for producing ammonia, NH3, from nitrogen, N2, and hydrogen, H2 gases. This process is crucial for the manufacture of fertilizers and various chemicals. Nitrogen is extracted directly from the air, which is about 78% nitrogen. Hydrogen, H2, is typically obtained from natural gas, methane, which is CH4, through a process called steam reforming. The chemical equation for the Haber process is N2 plus 3H2 produces and is produced by 2NH3. These are all in gas form. This reaction is reversible, meaning ammonia, NH3, can decompose back into nitrogen and hydrogen under certain conditions. To maximize the yield of ammonia, the conditions under which the Haber process operates are carefully controlled. The optimal temperature is approximately 450 degrees Celsius. Optimal pressure is around 200 atmospheres, and the reaction uses an iron catalyst. Let's understand the reasoning behind each of those conditions. In terms of temperature, the reaction is exothermic, meaning it releases heat. Hence, to produce more ammonia, a lower temperature is needed. According to Le Chatelier's principle, a lower temperature would favor the forward exothermic reaction, leading to a higher yield of ammonia. However, the actual temperature chosen of 450 C isn't that low. That is because lower temperature decreases the rate of reaction. While a lower temperature would produce a higher yield of ammonia, the reaction would be too slow. Therefore, a moderate temperature of around 450 degrees Celsius is chosen. This strikes a balance between a reasonable rate of reaction and a sufficiently high yield. Now, let's look at the pressure conditions in more detail. According to Le Chatelier's principle, increasing pressure favors the side with fewer gas molecules. In the Haber process, the forward reaction produces 2 moles of ammonia from 4 moles of nitrogen and hydrogen. To maximize the production of ammonia, high pressure is applied, shifting the equilibrium to the right and increasing the yield of ammonia. However, excessively high pressure would make the process expensive and hazardous, so a balance is struck, typically around 200 atm. This pressure provides a good yield of ammonia while maintaining economic feasibility. Finally, using an iron catalyst in the Haber process speeds up both the forward and reverse reactions equally. This allows the reaction to reach equilibrium more quickly without affecting the position of the equilibrium. This increases the efficiency of the reaction. This optimization ensures industrial feasibility, balancing efficiency and economic viability. Let's look at some extension knowledge on equilibria in the body. The equilibrium between oxygen and carbon dioxide in the bloodstream is essential for respiration. During exercise, CO2 concentration in blood is increased, as CO2 is a waste product of respiration. This increase of CO2 makes the blood more acidic. To restore the equilibrium, the body responds by increasing the breathing rate, which expels CO2 to bring the pH back to normal, and also draws in more O2 for further respiration. As well as this, at high altitudes, O2 levels are lower. Less O2 can enter the bloodstream. To compensate for this, the body produces more red blood cells, which can carry more oxygen, which helps to balance the O2 supply and demand. This constant adjustment is an example of dynamic equilibrium in biological systems. Understanding this balance and how these reactions occur is essential in the medical field, especially for analyzing respiratory conditions and treating patients properly. In today's lesson, we delved into the Haber process, an industrial method for producing ammonia from nitrogen and hydrogen gases. We examined the chemical equation for the Haber process, emphasizing its reversible nature. We focused on how specific conditions optimize ammonia production, a temperature of approximately 450 degrees Celsius, a pressure of around 200 atmospheres, and the use of an ion catalyst, and understood how these conditions favor the formation of ammonia. By carefully controlling these conditions, the Haber process efficiently produces ammonia, demonstrating the practical application of chemical equilibrium and Le Chatelier's principle in industrial chemistry. Watch the rest of the GCSE chemistry course at Sophos Education.